Grounding of meter bases is a critical aspect of electrical installations governed by the National Electrical Code. The use of split bolts on grounding electrode conductors, often referred to as GEC, is a point of frequent discussion and scrutiny. The NEC doesn't explicitly prohibit the use of split bolts on grounding electrode conductors. However, it stipulates that any connection must adhere to the requirements outlined in Section 250.64. Subsection D. This section emphasizes that the connection must be made following the manufacturer's instructions. Critically, the connecting device, in this case the split bolt, must be listed or labeled specifically for the purpose of grounding. This listing ensures that the connector has been tested and certified to meet the necessary standards for conductivity, mechanical strength, and corrosion resistance, all of which are vital for a reliable grounding connection. Regarding the isolation of meter packs, the NEC does not generally mandate treating each meter pack as an individual service when it comes to grounding. This is particularly true if all the meter packs are serving the same building or structure and are electrically interconnected. The underlying principle is that the grounding system should provide a common reference point for all electrical equipment within the building, ensuring that fault currents can be safely conducted back to the source. However, a key exception to this rule arises when meter packs are physically separate or electrically isolated from one another. In such cases, the NEC may require separate grounding systems for each meter pack. This is to prevent circulating currents and to ensure that each meter pack has its own dedicated path to ground, minimizing the risk of voltage differences and potential hazards. The NEC stance on multiple cold water grounds is tied to the size of the service entrance conductors. Specifically, the code mandates multiple cold water ground connections when the aggregate size of the service entrance conductors exceeds 1100 kcmil for copper conductors or 1750 kcmil for aluminum conductors. This requirement is rooted in the principle that larger service entrances are capable of delivering higher fault currents, necessitating a more robust grounding system to safely handle these currents. When the service entrance conductors are below these thresholds, multiple cold water grounds are typically not required. However, it's important to note that local codes or specific installation requirements may still call for additional grounding electrodes to enhance safety and reliability. In situations where multiple ground rods are being considered, the NEC stance is similar to that of meter packs. If the meter packs are part of the same building or structure, the code does not typically require separate ground rods for each meter pack. The primary goal of grounding is to establish a low impedance path for fault currents, and this can often be achieved with a single, well-designed grounding system that serves all the meter packs. However, even if not explicitly required, additional ground rods can offer several benefits. Firstly, they provide redundancy, meaning that if one ground rod fails or becomes compromised, the other ground rods can still provide a path to ground. Secondly, multiple ground rods can help to reduce the overall impedance of the grounding system, improving its ability to dissipate fault currents quickly and effectively. Thirdly, additional ground rods can help to mitigate the effects of soil resistivity, which can vary significantly depending on soil type, moisture content, and other factors. Based on common scenarios, it's observed that an inspector's findings are not always entirely correct. Regarding split bolt usage, split bolts can be used on grounding electrode conductors, but only if they meet the relevant requirements specified by the NEC. These requirements primarily revolve around the connector being listed or labeled for grounding purposes and being installed according to the manufacturer's instructions. The isolation of meter packs. Isolation may only be necessary if the meter packs are physically separate or electrically isolated from each other. If the meter packs are interconnected and serve the same building, separate grounding systems are typically not required. Multiple cold water grounds are only mandated when the aggregate size of the service entrance conductors exceeds the thresholds specified in the NEC. Multiple ground rods are not required, but they can offer benefits in terms of redundancy, impedance reduction, and mitigation of soil resistivity effects. When approaching grounding installations and facing differing opinions, consider the following recommendations. Firstly, thoroughly review the NEC handbook and any relevant grounding resources, such as the SOAR's book on grounding, to ensure a solid understanding of the applicable codes and best practices. Secondly, engage in open communication with the electrical inspector to clarify any points of contention and to address any specific concerns they may have. It's often possible to reach a mutually agreeable solution through constructive dialogue. Thirdly, consider revising the grounding system to address any potential safety concerns, even if the revisions are not strictly required by code. For example, installing additional ground rods or using multiple cold water grounds can enhance the overall safety and reliability of the electrical system. Grounding electrode conductors play a crucial role in electrical safety by providing a low impedance path for fault currents to return to the source, thereby facilitating the operation of recurrent protection devices such as circuit breakers and fuses. The size of the grounding electrode conductor is determined by Table 250.66 in the NEC, which correlates the size of the grounding electrode conductor to the size of the service entrance conductors. Proper sizing is essential to ensure that the grounding electrode conductor can safely carry the anticipated fault current. When connecting the grounding electrode conductor to the grounding electrode, it's imperative to use connectors that are listed and labeled for the purpose. These connectors are designed to provide a reliable, low-resistance connection that can withstand the stresses of fault currents and environmental conditions. The location of the grounding electrode is also a critical consideration. The NEC specifies that the grounding electrode should be located as close as practicable to the service equipment. This minimizes the length of the grounding electrode conductor and reduces impedance, thereby improving the effectiveness of the grounding system. Ground rods are a common type of grounding electrode, typically consisting of copper-clad steel or stainless steel rods driven into the earth. The NEC requires that ground rods be at least 8 feet in length and be driven into the earth to a depth of at least 8 feet. When multiple ground rods are used, they should be spaced at least 6 feet apart to avoid interference between the grounding fields. Cold water pipes are another common type of grounding electrode. The NEC allows the use of metallic water piping systems as grounding electrodes, provided that certain conditions are met. The water pipe must be electrically continuous and must be in direct contact with the earth for at least 10 feet. Additionally, the water pipe must be supplemented by an additional grounding electrode, such as a ground rod or ground plate. Concrete encased electrodes, often referred to as UFA grounds, are another effective type of grounding electrode. These electrodes consist of a bare copper conductor encased in concrete that is in direct contact with the earth. UFA grounds are often used in new construction and can provide a very low impedance grounding path. Ground rings are another option for grounding electrodes, consisting of a bare copper conductor buried in the earth in a continuous loop. Ground rings are typically installed around the perimeter of a building and can provide a very effective grounding system, particularly in areas with high soil resistivity. The inspection of grounding systems is a critical step in ensuring electrical safety. Electrical inspectors typically verify that the grounding system complies with the NEC and local codes. This includes checking the size and type of grounding electrode conductors, the type and location of grounding electrodes, and the quality of connections. Common grounding violations include improper sizing of grounding electrode conductors, use of unapproved connectors, inadequate grounding electrode depth or spacing, and failure to provide supplemental grounding electrodes when required. Addressing these violations promptly is essential to ensure the safety and reliability of the electrical system. Soil resistivity plays a significant role in the effectiveness of a grounding system. Soil resistivity is a measure of how well soil conducts electricity. Low soil resistivity is desirable because it allows fault currents to dissipate more easily. Soil resistivity can vary significantly depending on soil type, moisture content, temperature, and the presence of minerals. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to treat the soil to reduce its resistivity. Ground testing is a valuable tool for assessing the effectiveness of a grounding system. Ground testing involves measuring the resistance of the grounding system to earth. A low resistance reading indicates a good grounding system, while a high resistance reading indicates a potential problem. Several methods can be used for ground testing, including the fall of potential method, the clamp-on method, and the stakeless method. Transient voltage surge suppressors, often referred to as TVSS or surge protectors, are devices designed to protect electrical equipment from voltage spikes caused by lightning strikes, power surges, and other transient events. Surge protectors work by diverting excess voltage away from sensitive equipment and back to the grounding system. Proper grounding is essential for the effective operation of surge protectors. Bonding is the process of connecting together all metallic parts of an electrical system to create a common electrical potential. Bonding helps to minimize voltage differences and to provide a lower impedance path for fault currents. The NEC requires that all metallic parts of an electrical system be bonded together, including metal conduits, metal enclosures, and metal equipment housings. Equipotential bonding is a specialized type of bonding used in areas where people are likely to come into contact with water, such as swimming pools and spas. Equipotential bonding helps to minimize the risk of electric shock by ensuring that all metallic parts in the area are at the same electrical potential. Static electricity is the buildup of electrical charge on the surface of an object. Static electricity can be a nuisance and can even be a fire hazard in certain situations. Grounding can help to dissipate static electricity by providing a path for the charge to flow to ground. Electrocution is the act of killing someone with electricity. Electrocution can occur when a person comes into contact with a live electrical conductor and a path to ground. Proper grounding can help to prevent electrocution by providing a low impedance path for fault currents, thereby reducing the voltage on exposed metal parts. Electrical safety is paramount, and proper grounding is a cornerstone of electrical safety. By understanding the principles of grounding and following the requirements of the NEC, electricians and other electrical professionals can help to ensure that electrical systems are safe and reliable. Consider the specific scenario described, involving the installation of two 6-meter bases with built-in disconnects to feed power to a 12-unit apartment complex. The service risers each have a 350 kc male ungrounded conductor. The initial grounding approach involved running a 2/0 copper wire to the cold water ground, based on the combined size of the service entrance conductors, 700 kc male. This was followed by a #2 copper wire connecting the 2-meter base to the cold water grounding electrode using a split bolt. Additionally, a ground rod was driven and a #6 copper wire was used to connect it to the 2/0 cold water ground, again using a split bolt. The electrical inspector raised several objections. Firstly, the inspector stated that split bolts could never be used on any grounding electrode conductor, tap or not. Secondly, the inspector believed that each meter pack should be treated as its own service. Thirdly, the inspector required a separate cold water ground for each service. Fourthly, the inspector mandated a separate ground rod for each meter pack. Analyzing these points in light of the NEC and standard practices, the inspector's assertions are not entirely accurate. As discussed earlier, the NEC doesn't outright prohibit the use of split bolts on grounding electrode conductors, provided they are listed for the purpose and installed according to the manufacturer's instructions. The requirement to treat each meter pack as a separate service for grounding isn't universally applicable. If the meter packs serve the same building and are electrically interconnected, a common grounding system is typically sufficient. Multiple cold water grounds are generally not required unless the aggregate size of the service entrance conductors exceeds 1100 kc mil for copper, which isn't the case here. Requiring separate ground rods for each meter pack is also not a strict NEC requirement, although additional ground rods can enhance the grounding system's performance. Therefore, it is prudent to engage in a constructive dialogue with the electrical inspector, referencing the relevant sections of the NEC and manufacturer's specifications. If necessary, consider seeking a second opinion from another qualified electrical professional or consulting with an electrical engineer. Ultimately, the goal is to ensure safe and code-compliant installation while addressing the inspector's concerns. The NEC is updated regularly, typically every 3 years, to reflect changes in technology and best practices. Staying current with the latest edition of the NEC is essential for all electrical professionals. Numerous resources are available to assist in understanding and applying the NEC, including handbooks, training courses, and online forums. Local codes and regulations may also impose additional requirements beyond those specified in the NEC. It's important to be aware of and comply with all applicable codes and regulations. The use of qualified and licensed electrical contractors is essential to ensure that electrical work is performed safely and in compliance with all applicable codes and regulations. Proper documentation of the grounding system, including the size and type of grounding electrode conductors, the location of grounding electrodes, and the results of ground testing, is important for future reference and maintenance. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be checked periodically for corrosion and tightness. Grounding electrodes should be inspected for damage and deterioration. Ground testing should be performed periodically to verify the integrity of the grounding system. By following these guidelines, electrical professionals can help to ensure that electrical systems are properly grounded and that people and property are protected from electrical hazards.